Welcome to the BS and Beer Show. BS stands for Building Science. Thank you all for joining us. Like I'd like to say every time, pick everyone in the chat box and tell us you're here. Otherwise, nobody else knows that you're on here except for the panelists on the screen. So good evening and welcome to the show. Tonight's topic is refrigerants. What are we doing now and what should we be doing? So I'm really excited about this topic tonight. I'm Emily Mottram. I'm an architect here in Maine. I am drinking a gluten-free beer by omission, which is excellent. The BS and Beer Show is an independent grassroots movement. Everybody who joins us on the show, including our hosts, are volunteering their time to bring this information to everybody in the discussion and the fun. So please give a thank you to our guests and everyone who have been on here. And we want to give a big shout out and thank you to Fine Home Building and Green Building Advisor for helping us as our media partner to make sure this happens on Zoom every Thursday and gets up on our BS and Beer Show YouTube channel after the show. So Ben, off to you for some general announcements.
Hello, everybody. I'm Ben Bogey. I'm a project manager in Connecticut. And this evening I am chasing down a double shot of cold medicine with a Kent Falls Brewing Wavy Nature, which is oak aged ale with peaches. It's pretty tasty. So as Emily said, find the chat box icon at the bottom of your screen, post your questions and comments there. Be sure to click all panelists and attendees or everyone, depending on what it says. Otherwise, Zoom tends to revert to panelists only, which means only we can see your comments, or Mike Maines behind the scenes. Fine Home Building sends out Zoom reminders each week. If you want to receive those as well as other information, join our mailing list at the bsandbeershow.com or check out the weekly post at Green Building Advisor that goes up on Sunday mornings. If you have not been receiving the emails, please check your spam box. The video recordings of tonight's show will be available at Green Building Advisor, and all past shows can be found on YouTube and through the links at the bsandbeershow.com. An audio-only version of the BS and Beer Show is available on Spotify and Apple Podcasts. Additionally, we have a couple of media partners that we'd like to plug. The Brew Crew will be at the International Builders Show in February, recording live 2 shows. We have just confirmed we'll have Carl Seville and Michael Anschel joining us on the first show. And on our second show, we have Joe Stebrick, and we're trying to twist Christine Williamson's arm into joining him. So some great guests, really excited to be part of that initiative. Efficiency Vermont's Better Building Conference is coming up February 2nd to 3rd in Burlington, Vermont. Register before December 15th to get a discount. And then Nessie's Building Energy Boston Conference is February 28th to March 1st in Boston. And we'll drop links to all of these in the chat box. And finally, I almost missed it, Pretty Good House Graphic Handbook 2021 is by our friend Helen Watts and is available at the link in the comments. So this evening, we have John Harrod. John is the owner of Snug Planet, a home performance and weatherization contracting company in Ithaca, New York. John, what are you drinking this evening? Is there anything that we missed in that short bio that you'd like to mention?
Yeah, so I'm drinking a sparkling cider from the Finger Lakes Cider House. It's a local organic cidery here in Ithaca that was actually founded by one of my former employees. One of the things we do very well here in upstate New York is grow apples. And that it covers it. It's very exciting for me to be on this podcast here tonight. It's a great honor to be podcasting with Bryan Orr, whose YouTube channel I've learned so much from. And so, yeah, good to be here.
John, we're happy to have you. All right. And then secondly, Bryan Orr is co-founder of Kalos Services, a residential and commercial HVAC servicing company. And he started the HVAC School, which is a free training program geared towards professionals to be. Bryan, what are you drinking this evening? Is there anything we missed in that brief introduction?
Well, we'll start with what I'm drinking because I'm a Florida man. So I'm drinking Swamp Head, which is a honey cream ale. I've actually never tried it before, but it is, it's local and I'm actually quite impressed. It's really, really quite good. Yeah, I think the thing that most people know about me more than anything I do in HVAC is that I have 10 children. So I just got to get that out there before it comes up. And no, that has nothing to do with HVAC. Yes, I do know what causes it. And my wife does all the work. So there's all the answers to all the questions that everyone asks about that. Yeah. So yeah, thanks for having me on. This is going to be a fun conversation.
Your wife is an incredible human because I have
Indeed.
one and it about kills me. So I understand you guys may have a presentation or some things that you'd like to talk about. Happy to have you jump right into those or open up the conversation as however you see fit.
Sure, I have a couple slides here to share. So a lot of my interest in refrigerants sprung from climate change. And one of the things that's kind of a mantra right now in the climate change world is electrify everything. This was a phrase that I think was first used by David Roberts in an article in Vox. And the basic idea is that one of the fastest ways that we can reduce our emissions and get to a net zero economy is to replace everything that we're using fossil fuels for with electricity, whether that's space heating, water heating, cooking, transportation. And so then the question always comes up, well, isn't our electricity itself produced by fossil fuels? And the answer is yes, it is, or big parts of it, but that's changing. And renewable energy is becoming a bigger and bigger part of our electric mix. And so this gives us a clear path to transition to a zero carbon energy system over the next 20 to 30 years. There's also huge benefits in electrifying things like cooking and transportation when it comes to air quality. Gas stoves are responsible for a lot of nasty indoor air pollutants, including particulates. And electrifying our transportation sector is also going to do a lot to reduce smog. So when we look at the space heating sector, that's a place where air source heat pumps are a critical tool. This was a diagram that was made by our local extension agency, and they're very active in promoting electrification and heat pumps. And I threw it up here just to demonstrate the what refrigerants do in these systems. They are compounds that can absorb heat from low temperature outdoor air. And then there's a compressor which jams the molecules together, in the process raising the temperature. And so any heat that was absorbed in the cold outdoors can be released to the indoors. And then the cycle repeats itself. We go from a high pressure side where it's hot back to a low pressure, low temperature side. That refrigerant, which alternates back and forth between gas and liquid stage, comes back to the outdoors as a low pressure liquid. It boils off, absorbs more heat, goes through the compressor, and so on. And it's ideally a closed system. The refrigerants cycle around and around and around. In the process, heat is transferred from the cold outdoors to the indoors. That's in heating mode. In cooling mode, the process is reversed, and now the heat is absorbed indoors and rejected to the outdoors. So they can provide both heating and cooling. One of the reasons that they're so critical to electrification is that compared to electric resistance, they can move about 3 times as much heat for each, or they can deliver 3 times as much heat for each unit of electricity that's used. I just included a couple thermographs of an actual heat pump in operation, just to give you a sense of what refrigerants are doing. On the left, we have the outdoor unit, and you can see that the outdoor coils become quite cold. The refrigerant in there, the low pressure refrigerant, is boiling off and absorbing heat. It's going through the compressor and coming to the indoor head as a high pressure gas, where it's condensing, releasing its heat, and going back and around and around. And so this is kind of the magic of heat pumps. They are so far, historically been unusual in the Northeast, but with the development of high efficiency inverter based heat pumps, they're becoming incredibly popular in our area. So heat pumps are really key to efficient electrification, but we have to remember that the refrigerants that are used in this process are themselves really potent warming agents. R410A, which is the refrigerant that's used in most of the residential heat pumps that we're now putting in, has a 20-year global warming potential of 4,400, meaning that one molecule or one quantity of R410A, it's actually a blend of two refrigerants, causes 4,400 times as much warming over a 20-year span as the comparable quantity of carbon dioxide. Because it doesn't last as long in the atmosphere as carbon dioxide, its contribution over a 100-year span is less, but it's still pretty huge. A pound of R410A can cause about as much warming as a ton of carbon dioxide. So R410A and other HFC refrigerants are part of a group of compounds that we refer to as short-lived climate pollutants. This includes both the older refrigerants, the CFCs and the HCFCs, as well as the modern HFCs. Other important short-lived climate pollutants include methane, natural gas, and black carbon, which is essentially soot produced by the byproduct of burning biomass and fossil fuels. And it turns out that when we look at managing global warming over the term of the next 20 or 30 or 40 years, these short-lived climate pollutants are incredibly important. The long-term trajectory is really going to be shaped by our ability to curb carbon dioxide emissions, but over the next few decades, it's really the short-lived climate pollutants that are going to have a huge effect. There are policy initiatives that are underway to address these, including the Kigali Amendment to the Montreal Protocol. So the Montreal Protocol was agreed upon in 1987, probably the most successful environmental treaty of all time, to curb CFC refrigerants that were destroying the ozone layer. The Kigali Amendment, which was agreed upon in 2016, but it's not yet been ratified by the US, addresses global warming potential of refrigerants. It hasn't yet been ratified here in the US, but we do have the AIM Act, which was approved last year, and the EPA Significant New Alternatives Policy. Both of these are policy initiatives that are seeking to phase out the high global warming potential refrigerants and replace them with a new set of refrigerants that we'll be discussing tonight. And where the federal legislation has faltered, it was put on hold for a couple of years due to legal actions, although it's now back in place. State laws and regulations have also helped to push ahead the transition away from these high global warming potential refrigerants. I wanted to just really briefly give a little context so that we see how the current refrigerant transitions that we're talking about fit into the longer term history of refrigerants. In the early 20th century, some of the initial refrigerants that were used for air conditioning were things like ammonia, methyl chloride, sulfur dioxide. Things that had real issues with flammability and toxicity. Some of these are still used in other types of refrigeration, commercial, industrial, but they're really not used in homes anymore. Starting in 1928, chlorofluorocarbons were introduced, the original Freon. And these were actually a big improvement in terms of safety compared to the older refrigerants. But by the 1970s, we realized the damage that these were doing to the ozone layer, and that's where the Montreal Protocol, an agreement by over 100 nations around the world, agreed to the rapid phase out of these CFCs and their replacement, initially with hydrochlorofluorocarbons, HCFCs, which had a greatly reduced ozone depletion potential, but they still had some. So it was recognized that those two had to be phased out and replaced with HFCs, which have zero ozone depletion potential, but are still potent greenhouse gases. And so HCFC equipment, for example, R22 air conditioners, those stopped being produced in the US. In 2020, there was no more production or imports of R22. And so we're just working off the stock of reclaimed refrigerant. But now with initiative that was just introduced in September, we are moving ahead with the phase down of the high global warming potential HFCs like R410A used in most heat pumps today, with the goal of reducing those by about 85% by 2036. And the initial replacements that are approved by the EPA and are, undergoing active product development and rollout by industry are a set of refrigerants that are referred to as A2l refrigerants. You'll hear that term. Essentially, the refrigerants that we use today are A1 refrigerants, and the A1 refers to the fact that A, relatively non-toxic, and one, very difficult to burn. A2l are slightly flammable refrigerants. They've been used safely in Europe and Asia for years, but they do require some changes in equipment and some training and some additional precautions. Some of these are actually HFCs, like R32, which is a component of R410A, but on its own is slightly flammable. And some of them are things like hydrofluoroolefins, HFOs, blends that have a much lower global warming potential. So now we're taking, we're going from a global warming potential of over 2,000 for R410A to under 750 for all the new A2l refrigerants. And I think that's where I'll stop talking and turn it over for discussion and for Bryan.
Thanks, John.
So do you want me to go ahead and dive into some of that or go into? Okay.
Absolutely.
Sure. So my perspective, I'm going to be fairly controversial on purpose because it makes for better conversation. I'm not an extremist in any way. But here's the thing with refrigerants. They're not supposed to leave the system. Like it's a sealed system. So we spend so much time worrying about the global warming potential, and before that, the ODP, the ozone depletion potential of refrigerants. And yet we don't think about, I mean, I'm sure somebody somewhere is doing the math on this, but we don't think about the costs in production every time we have to ramp up a new refrigerant, every time we keep making these changes, what effects that has. And then in addition to that, the stresses that it puts on an already strapped industry in terms of the field technician. So one of the first things that I want to kind of put out there before I even talk further about, what makes good refrigerant and really kind of get into some of the techie stuff that I think will be interesting is why don't we do a better job of ensuring that the equipment doesn't leak? Because if the equipment doesn't leak, then we don't have to worry about it, right? I mean, you don't worry about your refrigerator leaking refrigerant. When's the last time you had to have your refrigerator recharged? Never. It doesn't happen anymore, right? And why is that? Well, it's because your refrigerator was made in a factory, right? And when you get done with it, you return it, and somebody in a facility does the recovery of that refrigerator. Why? Well, it's much easier to do it under those circumstances. It's much easier to deal with varying refrigerants. It's much easier to control the refrigerant. And so really what we're talking about is the entire Western world has embraced equipment that we have just accepted that it's going to leak. And even if it doesn't leak, then it's likely we're going to have inappropriate recovery practices in the field. In the HVAC world, it's the copper stub in the bucket of water. And that's, you'll see in the Facebook groups, like, haha, that's a joke. It's not a joke. It's not a joke. I would say 80% of the equipment, and this is a statistic made up on the spot, just like 90% of statistics are. I would say from my experience, 80% of systems are not being properly recovered. And so why do we embrace that as a reality? And instead, why don't we fundamentally relook at how can we create equipment and how can we hold manufacturers responsible to deal with this problem altogether. And of course, I also think we can greatly reduce the global warming potential of refrigerants by going to refrigerants that traditionally people are afraid of. But I think kind of reforming this conversation as far as what's possible would be really healthy for the industry, but also for the regulatory powers that be. Obviously, what tends to happen in a lot of these conversations, I know, building science folks aren't idealists. It's always practical, right? But what tends to happen is we throw around these ideals, but you recognize that when you have a completely distributed team with absolutely no controls in place, you can scream and yell all you want, but unless you have EPA agents at every corner, slapping cuffs on everybody, you're not going to solve that problem. So we're just pretending, we're just play acting. And when you look at the difference in dropping the global warming potential of certain refrigerants, we're going to drop it from 2,000 to 700. Yay. How about drop it to 0 by not venting it in the first place, by rethinking how we can handle refrigerants in a completely different way and start to think about different refrigerants altogether. And basically what I'm saying is self-contained equipment. The refrigerator is self-contained. The refrigerant is self-contained. It doesn't leak. It just doesn't. That's not the problem. The motor might fail, the board might fail, but it doesn't leak refrigerant. We have split systems all throughout the United States, and they leak refrigerant. And where do they leak refrigerant out of? Do they leak refrigerant out of the field fabricated connections? Not usually. They leak out of the factory evaporator coils. And why did they leak out of the factory evaporator coils when they didn't 20 years ago? Anybody know? It's because we're trying to hit arbitrary efficiency numbers with the equipment. And so we go to rifled aluminum and we stretch the metal really thin so that we can get really good heat transfer. And so it's, once again, unintended consequence on top of unintended consequence. If we're serious about solving global warming across, I don't care, politics, anything, if you're serious about solving it, then let's look at the doing things that will actually fix the problem, that actually really aren't that hard to do, other than the fact that the guts, the will to do it are kind of thin. So I want to dive quickly into, well, actually, I want to pause there and just see, because obviously I just said a bunch of super controversial stuff. So John, any thoughts on that, or anything you want to add in there? I swear this is my first beer. I said I'm not for it.
I'm just gonna say nothing sounded controversial to me there. That seems all very practical.
I was gonna say that sounded good.
Yeah, you won't get any disagreement from me. I think the refrigerator is a really interesting example. My refrigerator, which I bought last year, is charged with R600A, which is isobutane. It's basically not too different from the stuff in a cigarette lighter. And we can do that safely because it's a small quantity in a contained system, and we can use a highly flammable refrigerant safely in that context. And I think it's worth rethinking some of the assumptions about the way these systems are put together.
Yeah, so let's
we have clients add propane lines and natural gas lines into their house. Why is everybody? I know where you're going with this. Is why aren't we using those? Pardon me, the hydrocarbon, fuel style refrigerants?
Well, and I wonder,
it's just our fear of fire.
Yeah, are we using some of it incorrectly too, right? Like trying to expand its capabilities of what it can do by spreading it out, and how much of it is like, for our point on the HVAC stuff, right, is you, like you said, nobody's monitoring it, right? So we don't know necessarily. And how much of it is, well, it's in the manufacturer's instructions, but people just kind of aren't installing it that way. So, how much does poor installation also to, even if the manufacturer wrote it should be XYZ and triple evacuated and done all this stuff and whatever to try to create these more sealed systems, if they're not doing that and nobody's really checking, then,
yeah, where are the incentives, and right. So I'm going to back up and go into a little bit, just a really quick presentation on refrigerants, because I think this might be helpful. A lot of people imagine, and John already went through this a little bit, but a lot of people imagine refrigerants as these like magical fluids that get cold, right? I mean, it's like you run it through the tubing and then it just gets cold somehow. But really what a refrigerant is doing is it's constantly changing its state from liquid to vapor, vapor to liquid. And in doing that, it's releasing something called latent heat, or absorbing latent heat and then releasing latent heat. And that just means the heat energy that goes to change the state of something. Latent just means hidden. And so to change it from one thing to another thing, it doesn't change in temperature, it just changes in state. So if you can, put on your imagination cap here, and you think about your air conditioner in cooling mode, and you've got this evaporator coil inside your house, and this refrigerant is boiling as it goes through the evaporator coil. And everybody thinks boiling, that's hot. Well, no, actually, in this case, boiling is actually a process of absorbing heat. So the refrigerant in your evaporator coil boils cold, generally right around 40 degrees Fahrenheit. So what's unique about latent heat is that as it's traveling through that evaporator coil, it stays 40 degrees. As it's boiling, it's 40 degrees all the way through. It doesn't change in temperature as it picks up heat, in the same way that when you boil a pot of water, it's 212 as long as it's boiling. It doesn't get hotter than that, right? It doesn't change in temperature. So it's a really cool thing that we can do with refrigerants. Not only do they pick up a lot of heat, but they maintain a very constant temperature. If you think of using something like glycol or water, if you move that through a coil and say it's 40 degrees, it's not changing state. As it goes through and it picks up heat, what happens to the temperature? It starts to increase, right? And so that's what we call sensible heat. It changes in temperature as it goes through. So what makes a good refrigerant a good refrigerant? Get to the point here. Something called latent heat of vaporization. It means how much heat does it absorb when it changes from a liquid to a vapor. And then on the other side, if we're thinking about a heat pump in heat mode, you have something called latent heat of condensation, the heat that is rejected when it changes from a vapor back to a liquid. And so refrigerants aren't necessarily, generally aren't even as good as water in terms of their sensible capacity, how much heat they can move around in that way, but they are really magical in terms of how much heat they can move when they're changing state. And they also can do it under controlled pressures and controlled temperatures. So if we were to ignore the regulatory environment, if we were to ignore the fears, and we were just to say, what are the best refrigerants on Earth? What are the ones that just knock it out of the park because of their characteristics? The best, based on latent heat of vaporization, is ammonia. Why don't we use ammonia? Well, because it's very toxic, right? And you'll drive around, you'll see ice rinks, you'll see packing facilities, whatever, and you'll see the flag on top of the building that shows you what way the wind's blowing in case there's a giant ammonia leak and it creates death and destruction in its path.
So I can run the opposite direction.
So you can run the opposite direction, exactly. Yeah, so you know which way to run. Yeah, exactly. That's it. Yeah, well said. But those are massive amount. That's a massive amount of ammonia, right? In order to cool a residence using ammonia as a refrigerant based on its latent heat of vaporization, you would have far, far less ammonia than you would have R410A or its predecessor R22. So great refrigerant, toxic. So we got to balance that, right? What about R290? Anybody know what R290 is? It's propane. So we have this, and everybody's afraid of propane. You brought it up earlier. Oh my goodness, I cannot have propane in my air conditioner. I cannot have propane. Well, you literally have a giant tank of it and the side of your house that you let your kid light the grill. Everybody's comfortable with propane as long as it's sitting in a tank or as long as we're setting it on fire inside of our house to keep us warm. We're not comfortable with it for some reason when we circulate it and boil and condense it, right? Anybody's seen when you're doing a big outdoor grilling and the propane tank starts to get cold and maybe even frosty on top. It is a great refrigerant. It has great latent heat of vaporization. It has pressures that are very similar to R22. In fact, you could take an old R22 air conditioner. Again, this is, some of you probably still have one, and you could charge it with propane and it would work amazing. It would work better than it did with R22. It would just have, the little on the side risk that it might explode. So that would, that's not so great, but that's the thing. And so why is everybody so concerned about that? They're concerned about it because what if it leaks in the house, right? Why isn't anybody concerned about your gas furnace leaking in the house? Because you build it not to leak in the house. That's why the manufacturer is responsible to not allow it to leak in the house. Why aren't manufacturers responsible to not let evaporator coils leak in the house? Why? It's because we have developed this perverse incentive. The perverse incentive is hit this SEER rating, hit this HSPF rating, hit this rating, so that way you can stamp a sticker on it and everybody wants to buy it, right? They could solve the problem. They could make evaporator coils that don't leak. They didn't used to leak. They leak now. So we have to get honest about these conversations because we can solve this entire problem and we can solve it in one fell swoop. Kind of back to a text perspective, one of the things that is really important to recognize about this moving forward regulatory environment, we've got these refrigerants that have GWPs in the 2000 range, and now we're going to go down to ones that are below 700, right? Well, what's the result of that? It's not just one refrigerant. Carriers come out and said, hey, we're going to have one refrigerant. Daikin's come out and said, we're going to have a different refrigerant. What's the result of that? You think we have a problem with recovery right now? You're telling me that I'm supposed to keep 6 recovery tanks on my truck as well as 6 virgin tanks on my truck and recovery equipment to do all of it? What's going to happen? It's just going to get vented. That's what's going to happen. That's the result of this. You're making it worse by doing this. They are making it worse because nobody's answering the question. You ask the question, how the heck am I supposed to keep that many recovery tanks on a van? Oh, by the way, now I have to buy a semi so I can drive around. What's that going to do for global warming, right? So what's the solution to this? The solution is to stop playing with the same infrastructure that we currently have and just change the infrastructure. That's what happened with ductless. Ductless has its own set of problems. You're still running lines. You still have leaking evaporator coils, but we can see the benefit. It's a new way of building equipment. So imagine this. What happens if we have a self-contained heat recovery, heat pump, really, chiller. Chiller just means that it cools and heats a secondary fluid. And we keep that all self-contained outside the house. We can put ammonia in it. We can put R290 in it, propane. We can do whatever we want with it. It's outside your house, just right where the tank is for your grill. And instead of taking that and pumping that refrigerant into your house, we just use a secondary fluid. Glycol, water, whatever we decide. CO2 for that matter. We could use liquid CO2. That's what they do in some grocery stores. Whatever you want to use. Pump that into the house. You can use buffer tanks to heat your domestic hot water. You can do a hot deck, cold deck to reheat for dehumidification. You can solve every comfort problem, every dehumidification problem. You can heat domestic hot water at the same time, and you have a self-contained system that now is not going to leak because your refrigerator doesn't leak. It's the same thing. Charges less. It's done in a factory. When you're done with it, you send it back to a facility. They get the refrigerant out of it, right? That's the future, because now we don't care what's in it. In the same way that we don't care what's in your refrigerator. Nobody cares what refrigerant's in your refrigerator.
It's
we don't
like
care.
What we're doing with sanding units right now. It's, you're sending everything outside. It's one packaged sealed unit. The water flows out to the unit, gets heated, flows back into the building. One of the things that was kind of an aha moment for me, and I'm going to say this because it might help other people to understand this latent heat of vaporization is everybody knows a BTU is the amount of energy it takes to raise 1 pound of water 1 degree. Okay, Fahrenheit, so you do that up, Fahrenheit, up. You do that up until you hit 211 degrees, and then it takes an additional something like 900 BTUs to click that last degree. So that 900 BTUs is the amount of energy that's required for that latent heat of vaporization. So that I just wanted to throw that out there because it's a way for people to understand the physics that you're talking about.
Yeah, massive amounts of heat we can move around. It goes back to what John was saying about, it's generally 3 times the efficiency that you get when you're just going straight, watt to BTU conversion. So
is anybody building any systems like this, Brian? Is this
they exist? Archetype? They exist in Europe. I mean, it's like usual. These sort of things do exist. In Europe.
Can't get it here.
But what I'm saying is that we act like some of this stuff would be, oh my gosh, the investment's going to be so crazy. We're not talking geothermal here. Geothermal is an example where in a lot of cases, you got to drill a well. That's
a few of them.
Yeah, that's a significant investment, and that's a problem in and of itself, right? It's a whole different trade. This is not a different trade. This is not different skills than what the technicians currently have. This is nothing fancy. This is not complicated. Now, are there challenges? Yes, but they're no different than what you have with ductless. You've got to run some lines inside the house. You already have lines running inside the house. They're refrigerant lines, so they're going to have to be different lines. They might have to be a different size, right? Other than that.
So to take it back, right, because, some of us are in the Northeast and I'm going to get roasted in the chat box, whatever, is, all the way back to the very beginning when John was presenting and it was like, oh, there's heat outside in the wintertime, right? So like, how do we change this to heat? And then somebody else said that CO2, like, so say you had a CO2 only system, does that not do AC, right? This is where I start to lead to my inexperiences. Like, how do we get that totally outside unit, right? Because I've seen some of the stand-in systems and in really cold climates, do they work as well? I don't know. So I'm throwing that out there because I'm in the Northeast.
Can you give us a little rundown on CO2 as a refrigerant and some of the challenges that poses?
I mean, it's one of my favorite topics. We actually do work on CO2 in Florida on grocery refrigeration. So we do residential, we do commercial, but we also do grocery store refrigeration. And one of our customers uses CO2, which was a complete heresy 5 years ago. 5 years ago, they're like, you're never going to use CO2 in Florida. It's not going to happen. It's impossible. Forget about it. Because CO2 has this a couple of really strange properties. It has pretty good latent heat of vaporization, but it has something called I'm going to throw some really fancy words out here, but it's actually very simple. It has a very high triple point and it has a very low supercritical point or critical point. And what that means is that CO2, you know this about CO2. If you go to your grocery store and you want to cool something, you can buy dry ice. At least we can at Publix down the street. I can buy dry ice. And what does dry ice do? Does it turn to liquid? No, it's dry. It goes straight to vapor. It's sublimation. And so CO2 has this weird property where at certain points, it doesn't actually even have a liquid phase. So that makes it challenging to work with because we got to get it up to a certain pressure before it even has a liquid phase. That's the triple point thing. But then we also have this supercritical phase, which is kind of crazy because we always think, oh, there's 3 states of matter. No, there's not. There is infinite in between states of matter. And the supercritical phase is one of these where it stops behaving in the same way that it did when it was a liquid or a vapor, and it basically stops behaving by the rules of thermodynamics in terms of the sort of latent phase change. And so they become really inefficient is the point when it gets above about 86 degrees. And so the challenge is in markets that you need to do a lot of cooling, they don't work great. But in places like Canada, as an example, and a lot of European countries, CO2 is a perfect refrigerant when you're primarily doing it for heat pump applications. So kind of the other way around, it can be helpful because you don't want to get it, you don't generally want to get it more than about 70 degrees inside your home. So that 86 is kind of no longer a problem. But in, markets that really are the biggest consumers of power and refrigerants, air conditioning, like Florida, it makes it tough. Now, there are infrastructures where you start to use CO2 as a secondary fluid, and you can leverage a little bit of its latent capacity, but you're not condensing it up at that higher temperature range that it can be utilized. But to answer a simple question with a more simple answer, CO2 is a great refrigerant in this kind of narrow bandwidth. Where it's happy, and you get outside of that and it becomes kind of a terrible refrigerant, and it's also sort of hard to work with. Good news is it's good on the environment and it won't kill you. But if you compare it to ammonia and R290 propane, there's no comparison. It's not as good of a refrigerant as either of those.
In my limited knowledge, in my limited knowledge, I see, the CO2 heat pumps and stuff like that coming online. I'm like, why aren't we just switching everything to it? Because then we just have a parity of our GWP and our refrigerant there. But I do understand that there are some technical issues to have. And I've gone down the rabbit hole of trying to find CO2 heat pump systems that we can use in residential. And they're available in larger formats, but not quite small enough for what we need to do in residential.
Yeah, and there's another huge issue that
proven yet.
Yeah, that I didn't mention is that in order to work in the temperatures that we need CO2 to be in, the pressures are ridiculously high. You're talking over 1,000 PSI in a lot of cases. And so that changes the materials that you have to make the unit out of, and so that becomes a challenge as well. So again, I'm a huge fan of utilizing CO2, secondary fluid, some kind of special things, cold climates, great, but it's not going to solve the problem. I say it's not going to, but who knows? There could be some magical technological breakthrough. But just based on its thermodynamic properties, it has some enormous challenges. The other question that you asked, Emily, was about that kind of general question about getting heat from the outside. That's the thing that always kind of blows everybody's mind. But here's the basic idea: hot goes to cold, right? Heat moves from higher temperature to lower temperature. So all we got to do in order to get heat from outside into your house is make that outside coil colder than the outdoors. That's all we have to do. And there's a lot of heat outside, even when it's negative 20 degrees, because, we're nowhere near absolute zero. And until we approach absolute zero, there's a ton of heat available in that air. So the only thing is we just got to get that coil below that temperature. Does create some challenges because it tends to want to become icebound. So as soon as the colder we're making that coil, the more likely it is to become icebound. And that's where defrost comes in with heat pumps. But even that technology is evolving and getting better. And so heat pumps really they're the future. They can work in essentially every climate that we have. It's just a matter of figuring out ways to get that outdoor coil to a lower temperature than that outdoor air to get heat to move from higher temperature to lower temperature. I'm going to stop talking for a little bit there.
I was going to say, thank you. That's always mind boggling to people. And I feel like we have to have this conversation like every time. It's like, yes, at negative 5 degrees, there's still heat outside. It's perfectly fine. All of that stuff. So I appreciate you, kind of jumping into that a little bit more. It seems like there's lots of chat in the chat box about, some of these systems do exist, air to water heat pumps, where it really keeps the refrigerant in a more packaged unit. We talked about what, or some of it was what's the future? Like, this is a lot about what we're doing now. Where's it going? Like, what's the future of this? I don't know, John, if you had, any anything. And Bryan decided he's taking a break for 5 minutes. So go ahead and
So it seems like one direction that we're going to see over the next couple of years is a shift to air source heat pumps that are fundamentally similar to the ones that we have today, but they're using these slightly flammable A2l refrigerants. Those, they can't be retrofit into existing systems because you have to have various protections in place. You have to have inherently safe electrical components that won't spark. In larger systems, you may have to have some kind of active mitigation so that if there is a leak, it will shut down the system, ventilate the space, and so on. But I think major manufacturers are moving ahead with A2l systems, and we should start to see those maybe 3 or 4 years down the road. I do think this air to water technology, the kind of thing where we have a self-contained outdoor unit, and then we're moving the heat or the chilled water around the house with some kind of water-based fluid or antifreeze in our climate. I'm really excited to see more of that. I hope that those can become cost competitive. We were part of a little pilot study that did a couple of those a couple years back, and they ended up being challenging for a couple of reasons. One is that with the technology we had at the time, and I don't think it's changed a whole lot, you just can't get the kind of temperatures that you need to get useful amounts of heat out of hot water baseboard, which is our main hydronic distribution. So you have to look at either putting in more low temperature distribution, in-floor radiant, low temperature panel radiators, or air handlers, essentially things that look like ductless heads, but they've got the distribution fluid, the water, the antifreeze that circulates through those. So it suddenly becomes a big expensive project. And and the ones we did, the ultimate cost ended up being, not all that different than it would be to put in a geosystem after the tax credits and such were taken into account.
John, I've looked at some of those hypothetically looked at some of those air to water systems, and the thing that I run into is in the cooling season is delivering cooling to the house without there being condensation risks. And I know there's systems out there like the Masana, radiant cooling panels and stuff like that, but those are, like you said, they become incredibly expensive. Are there other technologies that you guys are seeing developed where we can use water as a fluid for cooling, or use glycol as a fluid for cooling? That
you absolutely can. You just have to run it through an air handler and have a condensate collection. You can't put it through a regular even a radiant floor in our kind of humid climates. So that's the approach that we've seen. There may be we may see some better ways to do that, and certainly in dry climates I think it's a lot more feasible.
I would say that's really interesting. When I was in college at Penn State, there was a professor that was trying out a dedicated air system, and we had these coolant pipes in these weird panels on the ceiling, and the solution to it was to keep it so dry in our studio so it wouldn't drip on our desks that everybody was sick all year round because it was so dry in our studio. It was, one, uncomfortable to be in there, and two, it was terrible. And the alarm system would go off if you'd open the window because then the humidity would go up. And so I'd love to see something that kind of solves that issue, that we can do that. It would be cool. I just, that's always what I think of when I think of cooling with radiant systems. And I was like, that wasn't such a great experience, but that's just for now.
Yeah, I'm not a big fan of radiant cooling. I think it's interesting because we already, there's so many advocates of heat pumps, right? I mean, throughout building science community, building performance, heat pumps are the way, right? They're the way of the future. But then everybody immediately goes to like the hydronic problem, the hot water baseboard problem, that issue. And well, can you replace a boiler with that? Well, that issue exists even today with heat pump technology. I'm kind of talking about a separate question. And the question is, how do we solve the refrigerant problem? And the refrigerant problem isn't about water versus air versus, it's all about self-contained refrigerant charges versus not self-contained refrigerant charges. And if we can solve that problem, see, this is where we can kind of lose the benefits here pretty easily, because you go down like, all right, what's the best refrigerant? Well, why don't we just go with the best refrigerant? The reason we don't go with the best refrigerant is because we're pumping it around the house. And so it becomes a safety risk. As soon as we stop pumping it around the house and now we keep it self-contained, now we can use refrigerants we previously thought we couldn't use. And that's the point. Are there these systems already that already exist? Yes, but they're mostly using R32. R32 is a good refrigerant. It's 50% of what R410A is made of. And so it's an A2l. You put R125 on top of it, which is a terrible refrigerant, but it's a flame retardant. And so you put it together, that's what R410A is. It's half a bad refrigerant, half a good refrigerant. Together, it's not flammable, right? So now we're saying, okay, hey, we have a really brilliant idea, this amazing technological advancement. We'll just do away with the bad refrigerant part and we'll just let it be kind of flammable. And now we're going to put it in your house. And it's not years away. It's right now. It exists today. These systems are already going in. Daikin's already putting them in. And I'm not scared. I think it's okay. I mean, they don't really propagate flame easily, but it just feels like we're getting a slight decrease. And it's not slight. I mean, it's significant. A decrease in GWP, but still high GWP. And now we're accepting flammability already. As soon as you accept flammability, you have to put all these protections in place because we're pumping it around the house. Stop pumping it around the house. We can now actually use refrigerants that are way better, which simultaneously increase efficiency. So now we're doing better on the efficiency side and aren't as bad if they were to leak, and they're much less likely to leak. So you're hitting it from 3 different angles. And that's where you kind of got to do it all at once. Like you can't keep, you kind of got to do all of those things at once, and then you solve all of these problems. And that's where, yes, you're still using air handlers. You're still moving air around. This does not solve the issue, to your point, John, of, radiant heat. That's the whole idea of radiant heat. There has to be pretty big temperature differences. Otherwise you don't get the radiant effect. It becomes localized and it doesn't heat the room and you're not comfortable. It's a horrible thing. And so you're not going to replace boilers tomorrow. We don't want to replace boilers tomorrow. We can't replace fossil fuels tomorrow, even if we wanted to, because the electrical grid isn't gonna support it. But to your original point, what problem can we solve? If we're serious about global climate change, we can solve the issue of refrigerants. We can solve that one much easier than we can solve an electrical grid that's not going to support everybody having a heat pump.
So Bryan, these are good aspirational goals that I think we need to continue to move forward to, but we're in a situation now where we're trying to make a difference at the moment. Yeah. So let me ask this, and it's kind of a very basic question. Are there systems that have a tendency to leak more than others?
Yeah, heat pumps have a tendency to leak more. And the reason is because you're taking an evaporator coil that you're normally operate. If it's a cooling system, it would operate, with 410A, it would operate, 140 PSI, something like that. And at 40 degrees. And now you flip it into heat mode. And what do? You jack that puppy up over 100 degrees. You have, pressures that are in some cases over 400 PSI. And we wonder why it leaks. The technology isn't different. They're not like, you'll have a technician come to your house and be like, yeah, it's a heat pump coil. They build it thicker. They make it so it's for the pressures. No, they don't. Not at all. They might test it at higher pressures so that way they can still sell it to you. They might do a burst test with it, but that doesn't tell you lifetime likelihood of not leaking. And it also isn't cycling it. What happens when you thermal cycle something between 40 degrees and 100 degrees over and over and over again? Expansion, contraction. What happens? Leaks, especially when the metal's thin.
I think you see where I'm kind of leading this question, though. So what are the options that we have at our disposal now to make more conscious choices and kind of mitigate risk as much as possible?
In terms of it's somebody who is
system selections, oversight of installation, manufacturer selection. I don't know.
Yeah,
commissioning.
Yes, it is. It's commissioning. I mean, it's making sure that all of the processes and procedures are being followed. But really, if you're wanting to thoughtfully reduce global climate change, then it's not about what happens when it goes in. I mean, it is, but not as much as what happens 5 years down the road when the evaporator coil leaks. And then what does the contractor do? I mean, we're in this interesting situation. There's this severe misunderstanding. Let's say one of you have an R22 system in your house, and that system, that's the refrigerant that, makes holes in the ozone, right? If that leaks, everybody believes that as a contractor, I'm not allowed to go in and just keep recharging it, right? There's got to be a law that prevents me from doing that. There is not. I could literally go back 1,000 times and put 20 pounds of refrigerant in that thing every 10 minutes and there is no regulation that
It's
prevents.
just going to get more and more expensive. That's the only downside.
Correct. So it costs. It's cost prohibitive
on the refrigerant. Yeah,
it's cost prohibitive. But I mean, at that point, if we're relying on cost drivers to make us do the right thing, well, then nobody's going to do the right thing on recovery anyway, because it's much more costly to recover than not to recover. And so that's the real way to actually make a difference is to be thorough on the back end as a consumer to make sure that people are following those proper practices. But how is that going to happen? And commissioning does matter. But honestly, the biggest factor that leads to coil leaks beyond manufacturing, which none of us are going to solve other than applying pressure to manufacturers. And if in the regulatory environment, that's what I wish we would focus our attention on. Instead of the technician in the field, put the regulation on the manufacturer and punish them for leaky coils. Then the problem is solved, right? But kind of back to that question, VOCs, increased levels of VOCs definitely increase evaporator coil leakage. It definitely is a contributing factor to formic corrosion on evaporator coils.
So that was one of the questions that popped up is, can you talk a little bit about formic corrosion? Because that's something that's been popping up across my radar quite a bit recently with issues. Can you explain to us what that is and kind of what goes into affecting how that happens?
Yeah, so formic corrosion is just it's ant nest corrosion. It's these tiny little corrosive pits that attack especially copper, but it can do it on multiple metals. What manufacturers have done to help is they've gone away from copper tubing, but copper tubing also has some other advantages over aluminum. So it's not, you haven't greatly decreased the amount of leaks, but going away from copper has reduced the formic side. But it's just chemicals, different chemicals that create acids and then kind of bore their way through the outside. There is some evidence that in some cases, poor practices such as failing to pull a proper vacuum when installing the system can lead to formic corrosion from the inside, but that's actually a lot more rare. And from just a completely personal experience standpoint, we see much, much higher cases of formic corrosion events early in the life cycle of a piece of equipment in foam insulation houses. So high efficiency houses, especially with the open cell.
Interesting.
We see it a lot, and we see it especially with ductless systems. So high performance. There was we had a case where there was one home that had a multi-zone system that went in of the same brand just down the street from another home. The only difference between the two homes was that one had open cell foam, the other did not. The open cell foam house, every 2 years, every evaporator coil was having to be replaced. And the other house, we had no cases of failure. So again, is that scientific analysis? No, but there's enough evidence of that occurring kind of over and over again that in the trade that's well understood.
Yeah, the one that I've seen recently is certain types of the insulation on the refrigerant lines. They're claiming are causing higher issues because guys aren't properly tape sealing the ends of them. It's allowing moisture to get in, cause a pH change.
And those are self-evident because that's where it's leaking, and that's not a normal place for it to leak. I mean, you peel that off, and there's greening all down the copper. But I'm primarily focused on evaporator coil leaks. Because those are the ones that are the most insidious, not only because they're so common, but also because they're very difficult to fix. You end up taking this large metal component that was made in a factory somewhere and you're just, tossing it because of that damage. And so it's a very costly thing on the industry as a whole, but then also environmentally.
Yeah, there's been a bunch of questions about how do foam and refrigerants relate, and also how do regions in the Northeast with more acidic outdoor conditions accelerate corrosion? Is that an issue in certain areas?
Well, I am not from the Northeast, so I am not so sure. I know that obviously we have acidic environments like coastal environments. That tends to be more galvanic corrosion. So there's cases where galvanic corrosion is where you get electrolysis between different types of metals, and that's what we see where the fins fall off of condenser coils in coastal towns after 5 years of operation, that kind of thing. So that's a factor. I mean, a lot of that is only mitigated through better quality construction, even things like all copper assemblies or all aluminum assemblies, so you don't have dissimilar metals and you don't get that galvanic reaction in there. There are solutions to all of these problems. It's always just a question of upfront cost versus lifetime cost. And when you play in, if you're doing just a cost benefit analysis, this is where we're at. People have done the cost benefit analysis and they're okay with how it is. But when you layer in the regulatory environment where a lot of times the regulations are made with a minimum of insight to the actual practices. That's that kind of tone deafness that leads to often these unintended consequences that I'm sort of wanting to point out. And again, controversially, because to your point, from a very realistic standpoint, what's going to happen? A2Ls are coming. That's what's going to happen. Probably isn't going to be a significant change in system infrastructure, at least over the next 5 to 10 years. And so we're just going to have to grin and bear it. But there's not going to be a significant change in the regulatory environment that actually makes recovery happen in the field, because that's what we're talking about here. You know, we focus a lot on commissioning, especially when you're making choices in design and building homes and all that. And you can do a perfect commissioning, but that doesn't change the fact that when the service tech comes back 5 years later, is he going to recover the refrigerant when he changes the evaporator coil, or is he going to use the copper stub in the bucket of water? And when he has to carry 10 different recovery tanks on his truck in order to service all the different equipment he works on, what do you think the possibility goes up or down that he's going to vent that refrigerant? Even if he wanted to do the right thing, what do you think the odds are that he's going to do the right thing when it becomes that difficult to do? Doomsday prophet. That's what I'm doing here. That's it's always great when you finish talking and everybody's like silence, and then it's like a tear.
Crash.
Yeah.
As we all blow up.
Yeah, exactly. Yeah.
You know, one thing that
Indian.
Yeah, one thing that I thought was really interesting was Bryan's working in a mature heat pump and air conditioning market where I think equipment failures play a bigger part in leakage.
That's true. Yeah.
We are a pretty new market, both for heat pumps and for central air in general. So we don't have the same base of experienced techs, and we also have, the average age of our system is a lot newer. So where we are, it's actually installer error that drives a lot of the initial leakage. And we have our state programs that are throwing, very large incentives for electrification. And I would like to see tighter requirements around commissioning. That I think that's one policy that could help. It turns out that to really properly test the system to make sure that it's tight, there's no one test that will do it. I think there's 4 tests that you need to do at the startup of each system. You need to do a standing pressure test. You need to bubble test all your joints, do a vacuum decay test, and then a final pass through with an electronic sniffer. And if you do all those 4, you won't catch every tiny leak, but you'll catch the vast majority of them. And so I would like to see some of our incentives tied to doing that full suite of testing and actually documenting it using apps and timestamp photographs and things like that. But we also in our area just don't have a great infrastructure for refrigerant management and recovery. It's our supply houses just don't make it easy to return reclaimed recovered refrigerant, and I think that's something that I think some targeted regulatory efforts could really help a lot.
Yeah, you make a good point. And on the multi-stage kind of leak detection, I agree with all of it other than the last one, the pass with the electronic leak detector, because that's the only one that you couldn't prove. And that's the one that would get pencil whipped. Like, you're not going to prove a negative on an electronic leak detection, and electronic leak detectors for tubing leaks, not really ideal anyway, because that's what you're looking for. You're looking at the connections that you made, and those are best tested by the 3 things that you said. I would throw in visual inspection as kind of the first step. So you make your connections, you do a visual inspection, you do a standing pressure test using digital tools, because that alone, doing a delta P test where you actually look at very minute changes in pressure that's temperature corrected, that alone is going to be probably the biggest thing, especially if you do it at higher pressure. A lot of techs are, literally pressurizing up to 20 PSI, listening for a hisser and then moving on. That's how a lot of it's being done. So when you go up to your minimum pressure, 250 PSI in that range, and you let that sit for even a half an hour and you see 0 decay, is it possible that you have a leak that only, is leaking when it's a vibratory environment or something? It's possible, but it's not normal. We see almost no occurrence of of leakage that is caused by us after our installs. And these installs aren't being done by 20-year experience technicians. These are being done by people in their 20s who are following proper procedures. So to your point, I think that's dead on. And it isn't actually even that hard to do. Like it's not asking that much of the process. If you compare it to things that we always are idealistically thinking air conditioning guys are going to do, like measure airflow, where it's not like, well, yeah, measure airflow. Well, how are you going to do it? I mean, it's like, okay, buy a true flow grid, I guess. There's no good way. This is actually a really well-established practice, and could be very easily regulated as part of, and again, my take on all of this is that sometimes regulation actually makes it worse. And this is what you see in places like California, where the amount of air conditioning equipment that's going in, the amount that's being sold versus the number of permits that are being pulled. We got to take a good look at completely redoing how we do the permitting process and making it a billion times easier than it is right now to do it. And so that way it's easier to regulate it, because as it is now, you can't compete if you're pulling permits in a place like California on residential homes. So you've created another perverse incentive. So working as hard as we can to get rid of the perverse incentives to actually incentivize the action that we want them to take, which is, again, it's helpful for the company to not have leaks, right? It's a callback. It's expensive. It's really good for everybody. It's a win for everybody down the line if you follow better commissioning practices like that. So yeah, it's a really, really good point.
Yeah, there's been a lot of great commissioning points on that. How do we change the infrastructure? How do we ask them for the things that we want? How do we make the manufacturers give us better things? Like, how do we provide better commissioning, especially in residential, right? I feel like some of this in commercial you'd never get away with, but in residential, it's kind of like, well, this is what we have. And then another question that popped up too was with heat pump hot water heaters is, one, it's inside. Is it more like our refrigerator? Have we just figured those out? Is it not a problem? And are we stealing heat from the inside of the house? Like, that's just another level of things that people are doing. So I don't know.
Yeah. I mean, in Florida, I absolutely love heat pump water heaters. I mean, they're amazing because I want to cool the house. That's what I want to do. So it's beautiful. It's a win-win. Is it a problem in cold climates? Sure. I mean, it is. It's making the space colder that it's in. Now, can you do other things? Can you take that air from elsewhere? Some designs you can, but that's where I think going to a truly centralized design where you basically every home has its own chiller plant. And this isn't a complicated, it makes it sound like it's not complicated. This is all this stuff exists, it's, you're just giving yourself options by having some buffer tanks, by having some things. So now you have those options, and that maybe doesn't in certain really cold climates with a lot of snow, maybe that doesn't preclude the necessity for having a very small boiler or something in place. Maybe that is necessary. And like I said, to not be so idealistic, we don't want all this stuff to change tomorrow anyway. It couldn't. All this stuff does have to happen somewhat incrementally. But I think that one of the best ways to move forward with this is to find ways to make it a win-win. Find ways to have conversations with the HVAC contractors where you're not so much browbeating them about the fact that they're killing polar bears, but that they're having callbacks and it's costing them money, and you're going to provide them with a way to help do that. And you're going to try to find a way to reduce some of that regulatory burden by doing things, using mobile applications, by using software. So it's not so difficult. So you're not having to fat finger things in. So you're not having to have a permit specialist on staff. I mean, this is one thing, anybody who's sort of excited about regulation, I always encourage them, spend like a month just pulling permits and see what that's like. And by the time of it, you're going to be a full out anarchist because you realize that it's so ridiculous. There's so much unnecessary process that could be summarized down, make people do the things they need to do in order to make houses safe, efficient, and properly installed. Photography is our friend, timestamp photography, Bluetooth connected tools. These things all exist. It's not that hard. We could do it. And I think it's just a matter of continuing kind of beating that drum to the extent that we have the power to do it. But, back to John's point, R32 is coming, HFOs are coming. That's what we're going to get next. It just doesn't solve anything. It just pushes it down the road, and it's going to be the next thing and the next thing and the next thing. Another tank we got to keep on our truck. Because this is the other thing. I know I keep coming back to this, but a lot of people imagine, well, you're not going to have to keep that many tanks in your truck because there's only 3 refrigerants that are going to be, and all the legacy refrigerants. that are still out there. 410A is still going to be out there. We're not making it illegal. R22 is still going to be out there. We're still going to be putting that in all the way up to 2030. We're still going to need to service those pieces of equipment. So it's more challenging than it may seem on the face of it for a service provider.
It's really interesting question though, because John started with electrify everything, right? And so you feel like in the car industry, like why do we have 16 different ports for how we charge our electric cars now that electric cars are going to be a thing? Like why are there so many different ways that we do it? Like should we be pushing the industry to pick a refrigerant? Obviously, as things get phased out, like we've got older ones, we want to try to recover them, obviously. So, you make a really valid point here, which is adding a bunch of new ones doesn't really solve our problem. So how do we get the, I don't know, manufacturers to talk to each other and just be like, pick one and move forward with one? If you're going to do it, if you have to make this thing, like, can't you all just agree to use the same one? Like, why do we all have to reinvent the wheel?
I mean, I think you understand it intuitively when I tell you that the players who are making it are DuPont, Chemours, Honeywell, Arkema. These are enormous corporations who have spent hundreds of millions of dollars in development on these products. So why don't they just all kumbaya, get together and just have one? It's the same reason why we have 3 different vaccines, or even more than that at this point. Because to some degree, that competitive side actually drives innovation, but there isn't innovation going on. I mean, that is a controversial one. I just made a lot of people mad at me. With refrigerants, there is not innovation going on. I don't want innovation. We have good refrigerants. We have great refrigerants that have low global warming potential, have zero ozone depletion potential, have really great latent heat vaporization, have really controllable pressures, right? They exist. We just have some safety issues that we can easily engineer around. So that's what I think we need to be forcing people to, or asking them to do.
And we don't want to be creating disposable systems, right? So that's essentially what the other things are. So instead of creating longevity systems, we're creating disposable systems that, now we've got to do the next thing instead of keeping this, working with this, improving this, making this a longer term lifespan, improving the quality of this one thing that we have.
Yeah, absolutely. And you see that, in electric cars, all of this stuff. As long as we're making progress, it's great. I mean, you see, for example, you see the way that Tesla just upended everything and innovated in ways that everybody would have said was impossible. And now that drives the industry forward. And that's what we need, is rather than people focusing on, the next private equity investment or the next merger or acquisition, which is what's going on in our industry all the time. The easiest way to squeeze a few more bucks out of it, have a little bit longer vision and say, all right, okay, let's start over here, and instead of just keep trying to get this just squeeze a little GWP out of it, let's actually solve the recovery problem. Because if we solve that, then it doesn't matter what we can put the most toxic chemical in the world in there, and if it ain't getting out, again, I'm not saying that's a good idea, but I mean, I think that fundamentally is the way that we actually get out of this thing, is stop worrying so much about what happens when it is vented and actually just prevent it from being vented in the first place.
I don't know how many people have heard this, but I know Tesla is actively going after the HVAC industry. So curious to see what happens there.
Yeah, and I'm all for that. I'm all for new players, new minds getting into it, and they'll bump into things that everybody else bumps into. But there are some major power players that have vested interests, and I don't think there's some cabal drinking blood and worshiping owls. And some it's just profit motivation. You've spent all this millions of dollars, and you're not, who's going to be the one to go to your bosses and say, yeah, you know what, R32 is the way to go. So we're just all going to get on board with that, or R290 is the way to go, because nobody makes money on propane. It's propane. It's available.
Everywhere.
It's everywhere.
Yeah.
Nobody makes money on CO2. Nobody makes money on ammonia. So there's a definite incentive to just keep.
It's like how we see the fossil fuel industries trying on to renewable energy now, because they figured out that there's a profit directive for them in order to do so.
Right.
They can make more money going that way.
Yeah.
Well, and I think that really brings up a great point. What you're saying is, like, we're coming up with new refrigerants. We didn't need new refrigerants. That wasn't what we needed. And I think the thing, about Tesla, whether you're pro Tesla or not pro Tesla, is they created an electric car that was always an electric car. It was never a car that they tried to convert from gas to electric to make it a car, it's always an electric car, right? So the technology is just a total shift, right? So instead of creating new refrigerants that are maybe better, like you said, like, let's just improve the fact that it leaks, or let's create a totally different technology, like something that's completely different, outside of the box, whatever, that at one point we thought was totally unreliable. Like, oh, this is a computer. It doesn't have an engine. It just drives itself, right? Like I think that's what they're missing here, is like creating a new refrigerant that has less, greenhouse gas potential is great. Sure, that's fantastic. Maybe we'll get there eventually, but let's make it not link first or totally different technology. Let's shift the game.
Yeah, and that becomes so evident when you actually start to look at the molecules that they're using, how little they are innovating. Like literally the big innovation now is, hey, R410A, it was two things. We're just going to make it half of what it was before. Hooray, that's innovation. Like, come on, really? And again, it's a good refrigerant. R32 is a good refrigerant in comparison to R410A, even compared to R22. But it's still just a silly compromise. And again, I'm not criticizing the manufacturers. Please don't stone me, manufacturer gods. I get it. Like I understand why this stuff happens. But it just, come on, we can do better.
Yeah, I agree 100%. And one of the things that we're up against is just the urgency of the climate crisis and needing to, make progress with the technologies that are readily accessible. It's this thing we've run into over and over again, whether it's compact fluorescent bulbs or high global warming potential foams, is that sometimes we end up with these suboptimal solutions and then we end up stuck with them for a long time.
Yeah, and that's the $1 million question, right? How do we change that? Like, we're all asking for it. We've all decided that this is, we need to, we kind of said, this is what we want. How do we get the manufacturers change? How do we change the regulatory procedures? Like, how do we, as industry professionals, choose different things to push those?
Keep stumbling along until we force the conversation to keep happening. Yeah. It's just like it's the natural path of progression. We're just going to have to keep bumbling along until we finally figure out how to stop, pardon my language, fucking things up.
Yeah, and I think also so much, and I've just done this entire time, so I'm the chief of sinners in this regard. But this isn't us versus them. It really isn't. I think some of it, especially when you're talking about people who are rank and file folks just trying to make a living, they're just like trying to do their job the best they can. It's the same thing that we saw when, consumers started consistently get blamed for the problems with the environment. And it's just like, you need to recycle more. You need to do this. And nobody said, and they are starting to now, but in the past, nobody said, hey, why aren't you actually being like charged based on the impact of the products that you're making and what you're making them out of? Like, why aren't you responsible for that person who actually made the product in the first place, coming up with a real good way to recycle this, or for a real good way for it to be truly biodegradable? How come we're not putting the responsibility there? Because that just makes more sense, right? Going to the source and saying, hey, source, you could actually fix this problem by doing it differently. And the answer is always cost, right? But that's so much easier to regulate at that level than it is to regulate the rank and file HVAC technician. And this is one of my favorite facts is, every HVAC technician has to be certified EPA 608 in order to handle refrigerants, proper recovery, all this sort of thing. But do you know how many regular HVAC technicians, just rank and file residential guys going around, who have actually been successfully fined or tried by the EPA? This is last time I checked. So maybe somebody's going to come up with one, but last time I checked, it is 0. So what's the point? We're literally making people do a thing, and it's just so that you can pass blame. So you can say, we did something, right? Now we feel good about what we did, with no actual care to really solving the problem. And I guess what I'm saying is that the more honest you are about what the real problem is, the more you can hold the people accountable who are actually causing the problem, honestly. And so much of this is actually what I really like about people who are really effective, and I think all of you probably fall into this category, really effective on the question of the environment and climate change and all of that. The most effective people say, okay, we are where we are. How do we actually fix this thing, rather than feel good about what we're doing? Those are two totally different things. You can regulate your way into kumbaya all day long, but where's the actual source of the problem? And my answer to that is, it's not in making life harder for the technician who's trying to make a living. It's in making their life easier. It's in making it easier for them to run a good ethical business, actually rewarding them for doing that rather than punishing them for not. And it's about holding accountable the people who are actually resulting in the biggest losses. Again, to John's point, I am talking about Florida, a market that is a much more, it was a very fair point, a market that we've had air conditioning and heat pumps for a really long time. I mean, I grew up, when I grew up, I started in the trade when I was 17. So I guess I did grow up. I grew up when someone said an air conditioner, I thought a heat pump, because that's just what we've had in Florida for the last 30 years. So it is true that we've gotten a little better at that side of things, at least keeping them from leaking on our front. But that doesn't change the fact that, like to your point, if you go to your supply house and you're like, hey, I want to return in this recovered refrigerant, they're like, oh, that tank's too light, that tank's too heavy, that tank's mixed with two different refrigerants. It's just like what we did with mercury. Like by the time we actually made it easy for people to turn in mercury bulb thermostats, there was barely any mercury bulb thermostats left. Nowadays it's easy, but it's like, okay, you know what happened to all those ones before then? They went into the landfill, and they're in the landfill today. The kids are at home playing with it in their hands, that kind of thing. So it's the same sort of thing. A lot of times we by the time we actually fix the problem, it's like we're now fixing the wrong problem because we're actually already beyond that problem. When I stop, it's very abrupt.
Tough questions.
Yeah, it's not very abrupt. It's just like everybody's like absorbing that, right? Taking it in and thinking about it and how the next thing, relates to that. And like you said, you grew up with it, and it's been a thing in Florida, right? I feel like it's newer for us in the Northeast that it is for you. But what's super frustrating for me is like you've been doing it for a while, and there's data and there's information, and why is the information flow not going backwards to the people who need to know that, right? Like if after installation, long-term leaks are the next biggest environmental issue because of exactly these things, like manufacturer defects in the parts, is like, man, how do you handle that? And, from the homeowner's perspective, like I have one project that, it's terrible to say, but there's a leak somewhere and we're not really sure where it is. And we don't know if it's in the coil, and we don't know if it's in one of our runs. And the installer was just like, we'll just recharge the system every year, which to me is like a total failure of like that. That's just, but there's absolutely, like you said, you could come back and charge it 1,000 times and there's no penalty to that. Right. But for the homeowner to go back to, maybe the parts are under warranty, but not the person who's going to replace the parts. Right. So it's still costing them thousands of dollars to replace a system that should have worked in the first place, but we've got defects in. I mean, hopefully it wasn't, somebody punctured something, a line set, whatever, during construction, but it could be leaky coil. I don't know, and like, that's the frustrating part.
Well, that's the beauty of your suggestion, Brian, about having everything as one package unit outside of the home, is because then if there is a failure, it puts the liability onto the manufacturer.
Yeah.
And then that tech and the company that has to come to service it and repair it has somebody to turn around and cover that cost, which then just it enforces them to push better and make it so that they have less leaks, because that manufacturer's going to want to incur less losses.
Yep.
So,
Right. And it'd be such an easy thing to prove at that point. Because right now it's just a finger pointing show. Oh no, it's the contractor. No, it's the manufacturer.
Right.
Yeah,
and then
the
if it's a bad install.
And then it's the
Right.
Yep.
Yeah. Man.
Are there resources out there that either of you can point to for us that are contractors that may not be as hip as you guys are as installers to ensure that we are getting a quality install?
Yeah, I'm actually releasing a video this week, and this is completely coincidental, but it's a complete 3D animated full condenser install video that talks about these best practices, proper brazing practices, pressure test, vacuum decay test, all this stuff. It's very heat pump specific. It's very Florida specific. But yeah, that's actually coming out. Should be next Thursday. And I have a lot of those sorts of resources on my app and on my website, hvacrschool.com. In terms of training the contractor, though, that's something that in home building, or even as a conscious homeowner builder, that's just something that has to be kind of embraced. I mean, it's I don't know if you all know my friend Bill Spone. He built his high efficiency home and put in a top of the line equipment and all this sort of thing, but it was fundamentally installed incorrectly, and it had a leak and it wasn't performing and all this sort of thing. And so just knowing the right way to do it, and even just hiring somebody who seems like they should know what they're doing, putting those expectations in place where they are going to report back as far as here, show me the screen grab from MeasureQuick or whatever application you're using to show that you did the decay test, to show that you did the pressurization test. And it would be great if there was, government backing of some of that that made it easy to do. But in the meantime, I think it is kind of imperative on us, who are actually building the homes to do that.
What I'm looking for is like a hit list of like what I need to ask my guy to prove. I've learned a fair bit of it over the years just from having to deal with it and from mistakes and shit that happen to kind of know when they're doing their job properly. But to have a resource like that available for other people is, I think that's tremendously helpful.
Yeah.
Yeah. And if it's Florida specific, John, we're asking for a New England specific one for you. Just what?
Yeah. So I have a couple articles that I can link to in the show notes. One is called Cold Climate Heat Pumps Do's and Don'ts, which was in Building Performance Journal last year. And the other is 4 tests to prevent refrigerant leakage, which is in Green Building Advisor. So I will include links to those when we send out the show notes.
Excellent. Thank you.
Do you guys see less leaks in packaged units like PTACs and RTUs than you do in split systems? I think I know the answer to this already, but just curious.
I do, yeah. That you still see leaks. Evaporator coils still leak because regardless of whether or not they're in the space, the air from the space is still traveling over them. So, and they're not fundamentally made differently. So it is both. But I think once liability becomes more of an issue, I think they'll take it a lot more serious to make sure that they don't leak. But to answer the question, they still do leak. And you still do see it. You just don't see the commissioning related leaks. So at that point, it's clear whose fault it is, or you would think it is, but then they end up blaming VOCs and Formic corrosion as well. So, but again, it's interesting. And so in their defense, it is true that there is more Formic corrosion now than there once was because there are more chemicals in homes than there once was. But, it's not like it's that different from the 80s to today. Again, I'm guessing here. And you would see systems from the 80s where the evaporator coils would last 20, 30 years. That wasn't the problem. Same thing with capacitor failure that we see this massive amount of capacitor failure. That just didn't used to be a problem. Different problems, but not that.
I'm just testing your hypothesis of the idea of making packaged units separate outside of the house. If that currently.
Yeah, it's still right, and it doesn't just taking a package unit and jamming R290 in it. It doesn't solve anything really. There are other factors too, which is that we once used mineral oil in R22 systems, which is a much more stable oil. It doesn't break down via hydrolysis. It doesn't have the issues. That was one of the things on the list that I didn't get to. Whereas now
we're talk a little bit about oil. Can you give us a couple minutes?
So really, there's fundamentally 2 different types of oils. Now there's more, but there was mineral oil, which was used forever, and that's the lubricant that moved through the system, lubricated the compressor and the other moving parts. But when we went away from chlorine-bearing refrigerants, so when we went away from HCFCs to HFCs, you no longer have the chlorine component. They wouldn't carry the mineral oil, and so we had to go to a different refrigerant, which is POE. POE is an ester oil, and if it has any moisture whatsoever, it breaks down via hydrolysis. It turns into an alcohol and an acid, which then basically eats the system from the inside out. And that's actually where we first, because before I started my company, I worked for a really large production builder, and we weren't doing anything the right way. Nobody had vacuum gauges on their trucks, and there was like no problem with mineral oil. It was like, sure, they probably weren't lasting as long as they should, but it wasn't a major thing. As soon as we went to 410A and POE oil, we started having compressors blowing terminals, black oil all over the place, because we weren't properly dealing with moisture and proper vacuum. So, and this happened, this is a long time ago. This is 2004, 2005, when this really started becoming a thing. And so we've learned through that you have to follow these practices when you have POE oil. It also is a solvent, so it scrubs any cupric oxide from the inside, the copper oxide from the inside, which is why we have to flow nitrogen while we're brazing. All these things that we always knew we were supposed to do, but we got away not doing, all of a sudden became a significant problem in warranty and all this. And it's not all specific to the issue with refrigerants, but it is another factor that gets thrown onto the service provider that didn't used to be a thing when we went to HFCs, and that continues. But for example, R290, if you went to R290, you wouldn't necessarily even have to use PE oil. Probably still would, because now it's ubiquitous. It's kind of the standard oil. But there's a lot of things like that have changed, that even within the industry, a lot of people don't understand fully. They don't understand the unintended consequences of making those changes. Where on one hand, it sounds good, but if you think about premature breakdowns in systems that now the refrigerant gets vented because there's a failure with the system that wouldn't have been with the older refrigerant, you kind of got to balance that. Layer in the fact that R22, which is the refrigerant before R410A, actually had a lower GWP. This is sort of the dirty little secret. The old stuff has a lower GWP. It just had a ODP, very small ozone depletion potential. And so we got rid of it because of its ozone depletion potential, but we actually went the wrong direction as far as global warming potential. And again, just layering in, like, there's all of these compounding factors, but we have good solutions. They exist. It's the good news. I'm going to try to end on a good note here. It's good news. We've got really good refrigerants. We can use them. We just have to stop being scaredy cats and build systems that don't leak.
And we've got good educators like John and Bryan out there in the world who are helping to inform the techs of the world so that we can install them properly. So
at least John. I mean, like I said, 50% of what I say is made up on the spot. So,
you're in Florida, so you get to do that, right?
Exactly. I am Florida man. Yep, exactly. Right. I'm drinking my Florida man swamp beer, and yep.
Yeah. No, well, I think there's a lot that you both said tonight, right? From different climates, different things, different approaches, and how you handle it, which is really awesome. That was a great way to end on a positive note on, like, it can happen. We can make it happen. And that, we need to read the articles. We need to know what to be asking our installers. We need to be pushing for the protocols to get better things from the people who are making it, so that it's not on our installation base and it's, from our manufacturers. So, did I learn a lot tonight.
I would just say too that it's important to remember that even with all the challenges that we have with refrigerants, the net effect of electrifying with heat pumps is really, really positive for the environment, because we're stopping fossil fuel build out, we're reducing CO2 emissions, and so they really are a great direction. And I think we can solve this refrigerant problem. We're just not quite there yet.
And Drew put a great comment in the chat box. He said, if we eliminate the loads, then we decrease the sizes of the system. So if we keep pushing to build better structures that are tighter and better insulated and fit their climate better, then we can reduce the amount of these systems that we have to use. Not trying to put you guys out of a job, but
But eventually
we have too much work, so I'm happy to reduce the workload.
I mean, it's going to be a while till we get there, but if we keep making strides in the right direction, it's all good.
Bryan, John, thank you guys. Has been tremendously informative, and we appreciate you guys taking some time out of your schedules to join us here, and look forward to following up in the show notes on GBA afterwards. Thanks a lot, guys. Everybody have a great night.
Thank you.
Thank you. Good night.